Hi, welcome to my series in nuclear and particle physics. So currently we are discussing accelerators. What are accelerators? So accelerators are machines or instruments that can be used to accelerate charged particles to very high velocities so that we can use those charged particles to perform a suitable nuclear experiment. So this is how the setup goes. You have incoming particles which are hitting on some kind of a target material. So you have incoming particles like protons or alpha particles or electrons or some other ions which are hitting on a target nucleus, and we can use this setup to perform nuclear experiments like high energy scattering experiments to look at the properties of the nucleus. We can induce nuclear reactions, or we can even break apart a nucleus and study the fundamental particles that make up matter itself. We can do all of this if these incoming particles have sufficient energy to overcome the Coulombic barrier. Now usually these kind of bombarding particles which are released in spontaneous radioactive processes do not have sufficient energy so that we can use them to create these kind of nuclear experiments. We need to accelerate these particles to very high energies so that they can be used to perform some kind of a desirable nuclear experiment so that we can study or gain information about nuclear physics. So the instruments which can do that, the machines which can accelerate such particles to extremely high energies which are desirable for nuclear experiments, such instruments are known as accelerators. Now in my previous video, I talked about a class of accelerators which is known as electrostatic accelerators. So electrostatic accelerators are those accelerators that can put these incoming particles in the presence of a static electric field so that these charged particles will accelerate because of an external electric field. So what usually happens is that if you have a charged particle, let's suppose of charge Q, which is moving in a particular direction, and you place this charged particle in the presence of an external electric field by creating two different terminals of positive and negative so that there is an electric field going on here, then based upon the potential difference between these two terminals, we can accelerate this charged particle to very high velocities. I showed in my previous video that the total amount of energy or the total amount of work done in moving this charged particle under this potential difference is basically equal to QV, where V is the potential difference between these two terminals, and this is in joules. All right. So therefore, we can accelerate a charged particle in the presence of a potential difference V to such high energies where the energy is basically given by QV, or we can write this in terms of NV electron volt, where Q is nothing but N multiplied by electronic charge. So what I want to show is that the total amount of energy that we can transfer to a charged particle in the presence of an external potential difference is basically directly proportional to the potential difference. So why I want to mention this is because the charged particles which are emitted in radioactive decay processes, in natural radioactive decay processes, have very less energies compared to the energies that we actually need to perform a nuclear experiment. The energies that we need to perform a nuclear experiment is of the order of millions of electron volts. Now that is actually a very high energy for a subatomic particle. An alpha particle, for example, to penetrate some kind of a large nucleus needs millions of electron volts of energy so that it can actually do that. So to transfer millions of electron volts of energy to a charged particle like an alpha particle, we need an electrostatic accelerator that can create a potential difference of the order of millions of voltages. Now that is not something which is easy. To create a battery that can maintain a potential difference of the order of millions of voltages, it's not something easy. Therefore, scientists devised different kinds of machines or accelerators, at least in the case of electrostatic accelerators, where we can generate a potential difference of the order of millions of voltages by some other kind of a mechanism. So one example of that kind of an accelerator is the Graaff Generator, which was created by a scientist by the name of Graaff in 1929. A Graaff generator is simply an electrostatic accelerator that can create potential differences of the order of millions of voltages. Almost around 5 millions of voltage differences can be created by Graaff generators. So in this video, I'm going to talk about the principle, the working mechanism, and the construction of a Graaff generator, as well as some alterations to the Graaff generator that is also made these days, which is the Tandem Accelerator and the Pelletron Accelerator. So I'm going to discuss all of them. So let's first talk about the Van de Graaff generator. Now you usually might have seen the Van de Graaff generator in some other context. For example, the Van de Graaff generator is quite popular in science education or in entertainment. The small Van de Graaff generators, which are used for educating students about science, can reach potential differences of the order of up to 100,000 voltages. But the larger Van de Graaff generators are usually used for the purpose of accelerating charged particles to perform some nuclear experiment. Now, what is the principle on which this kind of a generator is based? Let's discuss that first. So the principle on which a Van de Graaff generator is based is quite simple. If let's suppose that you have a conductor which is charged, that means let's suppose this conductor has let's suppose positive charges. Now, if I bring this conductor in the presence of some kind of a external hollow metallic conductor. So if I bring this conductor in the presence of some kind of an external hollow metallic conductor, I connect these, what is going to happen is that a very interesting thing is going to happen. These charges on the inner conductor are automatically going to get transferred to the outer surface of this hollow conductor. So you see what is happening here. The charges which were originally in the inner conductor will automatically get transferred to the outer surface of this hollow conductor. Now, why does that happen? We know from electrostatics that the electric field inside a conductor is zero. There cannot be an electric field inside a conductor. So if there are free charges inside a conductor, then those free charges are always inclined to move on the outer surface of the conductor. So when we have this kind of a system where we bring a conductor which has charge in it and bring it in contact internally to a hollow conductor, then all the charges are getting transferred to the outside surface of this hollow conductor. It does not matter what is the potential of this hollow conductor. We can theoretically keep on adding charges over and over again to this hollow conductor and increase the potential of the hollow conductor to very, very high values. So this is the basic principle with which a Van de Graaff generator works. It works on the principle that when a charged conductor is brought internally in contact with an external hollow metallic conductor, then all the charges can be transferred to that outside surface of the metallic conductor. It does not matter what is the potential of that metallic conductor. We can cumulatively keep on adding charges to that metallic conductor and increase the potential to very, very high values. So using that principle, first let's understand this construction. So here you have this kind of I have drawn it here as a dome structure, but it can also be as a spherical structure. So this is a metallic hollow, some kind of a conductor, all right? So this is a metallic conductor or a terminal which is in contact with this kind of a conveyor belt. So you know conveyor belt, this is a conveyor belt which is connected to wheels and it is strapped by some kind of a rubber charged conveyor belt. All right, it's made up of an insulating material like rubber. So let's ignore this for the time being. This entire thing could be housed in some cases in a pressure vessel which is filled with some kind of an insulating gaseous medium like sulfur hexafluoride. For small Van de Graaff generators, this outer housing might not be there. For large Van de Graaff generators, this outer housing is necessary. So let's first understand the construction. You have this hollow metallic cylinder which is connected to a conveyor belt. On one side of the conveyor belt, this is connected to the hollow metallic cylinder by a comb-shaped electrode. So you have an electrode which is connected to this conveyor belt by a comb-shaped structure. I'll explain why the comb-shaped structure is necessary. On the other hand, this other end point of the conveyor belt is connected to another comb-shaped electrode which is connected to some high DC potential, a positive DC potential. So because this is connected to a high DC potential, it is basically connected to positive terminal. So let's first understand why a comb-shaped structure is used. So a comb-shaped structure usually has spiky endpoints. The reason is that for the transference of charge from one material to another, it is beneficial to have spiky or pointy surfaces. This is because we know from electrostatics that the surface charge density in pointy surfaces is greater than the surface charge density in less pointy surfaces or blunt surfaces. So from electrostatics, we know that the surface charge density is inversely proportional to the radius of curvature of the material itself. So what basically it means, simply stating, is that so the surface charge density on a surface which is blunt is less as compared to the surface charge density of pointy surfaces. So compared to this surface, the surface charge density in these pointy surfaces will be very, very high. What this does is that it creates a situation where transfer of charges becomes very, very easy. All right. So quite simply put, when you have pointy surfaces, we can easily transfer charges to another kind of a surface using pointy surfaces. So what happens in our case is that when we have this comb-shaped structure connected to a high DC voltage, then of course positive charges gets accumulated in this comb-shaped electrode, right? So there is a huge amount of positive charge that gets accumulated in the comb-shaped spikes. Now what happens is that because of these positive charges, initially the conveyor belt is neutral. So the negative charges from the conveyor belt will now transfer to the electrode. So the negative charges will transfer to the electrode, which will basically make the conveyor belt in this region positively charged. Yes, so in a way there is a transfer of positive charge which has happened from this high DC potential to the conveyor belt. Now the conveyor belt in itself is moving. Yes, so the conveyor belt is moving in this particular direction. So the moment the conveyor belt becomes charged, these charges now move upwards. So as these charges keep on moving upwards, finally it comes in contact with this hollow metallic conductor here. So as I explained to you, because of this principle, the moment it comes in contact with this hollow metallic conductor, what happens is that again electrons from the hollow metallic conductor will get transferred to the conveyor belt. So the conveyor belt surface again will become neutral, but however this will effectively mean that these positive charges are getting transferred to the outside surface of this hollow metallic conductor. So quite simply put, the working mechanism of this kind of a setup is quite simple. This comb-shaped electrode is connected to a positive terminal. It leads to the transfer of positive charges to the conveyor belt. The conveyor belt now moves to the other end where these positive charges are immediately absorbed by the outer conductor and redistributed on the outer surface of this metallic conductor. And by performing this action over and over again over a period of time, we can essentially accumulate a large number of positive charges on the surface of this terminal here, so that we can essentially obtain potential differences of the order of millions of voltages. So here you see this conductor itself is at, let's suppose, a positive potential, while let's suppose here we have ground which is at zero potential. We can keep on performing this action so that the accumulation of charges on this conductor is so high, it is such a huge amount of accumulation of charges that the potential difference can reach up to the order of 5 million voltages. And then we can use this setup as an electrostatic accelerator. So here we have this accelerating tube where there is an ion source initially, which is ion source is, let's suppose, emitting some kind of a positively charged particle like an alpha particle or maybe a proton. So the moment these positive charged particles are emitted, they are now present in the potential difference of plus V voltages, which is of the order of, as I just now said, 5 million voltages. So they are present in the potential difference of millions of voltages. So these particles will now get accelerated to extremely high velocities. They will gain energies of the order of millions of electron volts. So now they can be used or directed to some target nucleus to perform a necessary or a desirable nuclear experiment. So this is how a Van de Graaff generator can be used as an electrostatic accelerator. Now Van de Graaff generators are quite popular because these are some of the earliest accelerators to attain potential differences of the order of millions of voltages. However, one small disadvantage is that we cannot keep on adding charges infinitely in a practical manner, because after some time leakage of charges start happening. So we can keep on increasing the potential difference only up to that point where the rate of transfer of charges is equal to the rate of leakage of charges. Also, another disadvantage of Van de Graaff generator is that we can only use this kind of a setup for the sake of positive charges. So we can use it for protons, for alpha particle or positively charged ions, but not for the sake of negatively charged ions. Now, if you are looking at this setup, we can alter the setup to create even greater amount of accelerations. How? Just look here. So this is at plus V voltage. This is at ground, and let's suppose this is also at ground. Now, if we can devise a mechanism where, let's suppose, we have a negatively charged ion which is introduced here, then this negatively charged ion will be accelerated up to this point because of attraction, and when it reaches here, if we can somehow strip away the electron from the negatively charged ion and make it positively charged, then now this positively charged ion will again accelerate up to this particular point. So basically a negatively charged ion can accelerate once and it becomes positively charged because of some stripping kind of a material, and then again it accelerates to obtain twice the acceleration which was originally obtained in the Van de Graaff generator. So these Van de Graaff generators in modern times are usually modified into what is known as other kinds of accelerators. So in a case of a tandem accelerator, the acceleration is twice that which is obtained by a traditional Van de Graaff generator. So to explain tandem accelerator, let me redraw this diagram a little bit. So I have essentially redrawn this metallic conductor because now this accelerating tube is twice its length. So as you can see here, the accelerating tube starts from here at ground potential and it goes through the metallic conductor with a potential of plus V, and then again it ends here at ground potential. So this is a tandem accelerator in which the ion source usually emits negatively charged ions. Let's suppose hydrogen minus or a helium minus or an oxygen minus. Now these negatively charged ions basically get accelerated from 0 to plus V, and they achieve an energy which is of the order of around 1 voltage electron volt, because the charge is 1 in these cases. V is the potential difference, and this is in terms of energy of electron volt. So they will experience an acceleration of the order of 1 times the potential difference. Now the moment these negatively charged ions come here, they pass through something which is known as stripper. So a stripper material is like a carbon foil or some kind of a container containing a gas at low pressure, which can effectively strip away the excess electron from these ions. So the purpose of a stripper material is that they can strip away the excess electron from these ions. So now these ions, after passing through the stripper material, will basically become neutral, H or He or O. But that is not sufficient because neutral particles cannot get accelerated in the potential difference. So we need to strip them of another electron. So if you strip them of another electron, then this becomes H plus or He plus or O plus. Now, if the stripper material strips away twice the number of electrons in any of these negatively charged ions, so the negatively charged ions, once it reaches here, once it gets accelerated, is stripped away from 2 electron. Now they can again accelerate it from plus V to 0 V. So they can again experience an acceleration and increase their energy by 1 V electron volt. So what is the total amount of energy provided to the initial ion? So the total amount of energy provided to the initial ion is 1 plus 1 electron volt. Yes, so 1 plus 1 V electron volt. So 1 plus 1 multiplied by the potential electron volt, or twice the potential of the electron volt, which is double the amount of energy that a normal Van de Graaff generator can provide to these ions. We can even increase the amount of energy by stripping these ions further. So you can strip, let's suppose, the He to He2 plus, you can strip the oxygen to O, oxygen 2 plus or oxygen 3 plus, and if you do this, then basically the total amount of acceleration experienced or the total amount of energy gained by these ions will be of the order of 1 plus n V EV, where n is the number of charge of this kind of an ion. So as you can see here, by stripping away some heavy ion further and further, we can increase the total amount of energy that this kind of an accelerator can basically provide. So a tandem accelerator is more beneficial compared to a normal Van de Graaff generator because it can provide more than twice the acceleration, or it can provide more than twice the amount of energy to the incoming particles by using the same setup, basically. So most Van de Graaff generators used in today's accelerators are usually tandem accelerators, where the negatively charged ion is stripped away from two electrons and then again it is accelerated because of a positive potential difference. So tandem accelerators are better than Van de Graaff generators because they can provide double or greater than double the amount of energy to the incoming particles, but they have a limitation that they can only be used in those cases where the ions can be negatively charged and they can be stripped away of the electron by some stripper material to create a positive ion during its journey itself. Another alteration to these kind of tandem accelerators are known as Pelletron accelerators. So the Pelletron accelerators are basically distinguished from normal tandem accelerators in the sense that the conveyor belt is made up of a different kind of material. So usually in normal Van de Graaff generators, the conveyor belt is made up of some rubber or fabric kind of a material, but in the case of Pelletron accelerator, the conveyor belt is actually a chain. So the chain is made up of small metallic cylindrical tubes which are connected by some insulator material like nylon. So you have small metallic cylindrical tubes which are connected to each other by some insulating material like nylon, and this, instead of a belt, you effectively get a chain which is transporting charges over and over again. So it is these small metallic cylinders which get charged here, and it is the small metallic cylinders which gets discharged at this particular point. The benefit of this kind of a setup of using a chain of small metallic cylinders which are known as pellets instead of a rubber belt is that you can have a greater velocity of this kind of a system where the transfer of charge happens at a greater rate. A Pelletron accelerator can charge up quickly and has a better energy resolution. In India, we have two Pelletron accelerators, one in Tata Institute of Fundamental Research, TIFR, which can reach potential differences of up to 14 million voltages, and another is at Inter-University Accelerator Center in Delhi, which can reach potential differences of up to the order of 15 millions of voltages. So that is all for Van de Graaff generators. I hope you have understood something about the principle, the working mechanism, and the construction of a Van de Graaff generator, as well as a tandem and a Pelletron accelerator, which are effectively used as accelerators to accelerate charged particles so that these charged particles can be used for bombardment onto some target nuclei that can create some kind of a desirable nuclear experiment, like high energy scattering experiments to study the properties of a nucleus, to study the size of a nucleus, like inducing some kind of a nuclear reaction, or to break apart a nucleus and studying the fundamental particles constituting it. That is all for today. I hope you have learned something. Thank you very much and see you in the next video.